Hey, welcome everyone to our Winter 2023 series of OTF Connects webinars entitled Animating the Revised Math, Science and Technology and Science Curriculum. My name is Peter Beans and I'm honored to be your moderator for today's session with Laura Wodlinger entitled Coding and Engineering Design Process in the SNC1W, Practical Strategies for Classroom Teachers. Before we begin, I'd like to do a land acknowledgement. We acknowledge first and foremost that we are gathered in the province of Ontario on the traditional territories of various Indigenous peoples who have been present on this land known as Turtle Island since time immemorial. More specifically, the location of this event is Mississauga, which is in the Dish with One Spoon territory. It is the traditional territory of the Wendat, Mississaugas of the Credit First Nation, Haudenosaunee, Wyandot, and Métis peoples. We acknowledge that this has been a meeting ground for generations. We are grateful to the stewards and caretakers of this land. As advocates, teachers, and educators, we understand our collective responsibility to honor, protect, and sustain this land. We further recognize and honor within the membership of OTF and our participants at this event who are not Indigenous to this land. Who are Indigenous to this land. This practice of recognizing the ancestral and traditional lands in which we work, live, and play is a concrete action that we undertake as a first step towards reconciliation between Canadians and the Indigenous peoples of this land. But it is not our only step. Collectively and individually, we must seek to denounce the injustices and wrongs that have been committed against the First Nations, Métis, and Inuit peoples, and to dedicate ourselves to cultivating and maintaining relationships based on mutual respect and truth. With that, I'd like to introduce our speaker today. Laura Wodlinger is the Director of Secondary Resource Development for STAO, the Science Teachers Association of Ontario, a regional teacher leader with Let's Talk Science, and a secondary school and de-streaming support teacher in the York Region District School Board. She describes herself as a citizen scientist, amateur tap dancer, karaoke enthusiast, and full-time nerd. And with that, I'd like to turn it over to Laura. I will stop sharing.
Thank you, Peter. Okay. So welcome, everyone. I'm so glad I get to do this with you. And I am excited to help you move forward with coding and engineering design for the new grade 9 de-streamed science class. If you want to scan the QR code on your screen, or if you want to enter tinyurl.com/OTF2023 then that will take you to the slide deck. You don't have to, but you might want to. And I'm sure Peter will throw the link in the chat for you.
I will do
that. So just in case you don't know who STAO is, the Science Teachers Association of Ontario, many of you probably have memberships through your board, whether you've activated them or not. But we provide classroom resources, PD, networking, everything kind of that science teachers might need to be better science teachers. So feel free to check that out if you haven't already. Don't do that, Laura. So once again, this is me. I'm happy to provide any additional support after the presentation, and I'll put all of my emails and socials at the end of the presentation. But I'm a full-time high school teacher in York Region District School Board, and I volunteer with STAO for secondary resource development. So when the new grade 9 de-streamed curriculum came out, I was all over it trying to figure out what new teachers and experienced teachers might need. And that's led to this presentation. So here's the goal. The goal is to give everyone a place to start. And if you already had a place to start, kind of what your next steps could be. So we're going to talk about both coding and engineering design, what they are, how they work in the curriculum, and how you can actually integrate it successfully into SNC1W. So where it fits in the curriculum, how to actually do it and assess it, things like that. And I believe we have our first poll. Peter, if you'd like to launch that. I would really like to know what drew you to be here today. So feel free to select as many as are reasonable. Perfect. You are all in the right place, and so am I. Okay, that sounds perfect. So we're all here for specific ideas, assessment, and a way to get started. Great. Okay, so we're going to get started by talking about why coding. Coding is basically the ability to talk to computers. And it might seem like that's a really specific thing. You're going to be a computer programmer, but it has a lot of transferable skills. And so ideas like creativity, problem solving, analytical thinking, which is super useful in science, pattern recognition, which is also super useful in science, as well as just resiliency, letting kids persevere and struggle a bit productively. It also demystifies technology. Technology goes from being a mysterious black box to something that's actually understandable, which is really a good thing and one of the other goals of science. Huge cross-curricular applications if you like working with other teachers in your school, or if you happen to do any intermediate work where there is a lot more cross-curricular going on. And it's also needed for a lot more careers than students give it credit for. The other thing I like about it is that it's very easy to differentiate, whether students have never heard of coding or whether they're already experts at several programming languages. Pretty much every coding activity easily works across multiple levels with basically no effort from the teacher, which is pretty awesome. As far as it being needed for many careers, if you ask students what their coding can be used for, most of them will give you two answers: computers and phones. And there are far more than that. But before I get into it, can we launch our second poll?
Launching away.
So, how familiar are you with coding? At the beginning of September, I knew virtually nothing. So, come a long way. Okay, so a little bit of familiarity in the group. Quite a few people not familiar at all. That's totally fine.
Okay,
You will leave today having moved up a category.
I'll just end the poll and then I'll share the results.
Yeah. Okay. So we got quite a range, but mostly in the somewhat familiar category. So if you ask students what coding is used for, computers and phones, in reality, it's basically everything nowadays. And kids really don't understand how ubiquitous, how common coding is now. And things they use every day: elevators, traffic lights, washing machines, social media, all of it relies on microchips and coding instructions. And so this is something that can really be applied in pretty much any career at all and be a benefit. So through the curriculum, coding was recently added to the K-8 curriculum, or 1 to 8. And it's very much a case of students learning a particular aspect of coding every grade. And so you can see, in grade 1, it's sequential events. So, okay, I want to start my car. Step 1 is unlock the door, then open the door, then get in the car, then put my foot on the gas, then press the start button. It's breaking down a task into smaller tasks. And as they go through the grades, they learn slightly more interesting things like repeated events or conditional statements. If it's raining, bring an umbrella, right? If it's sunny, don't bring an umbrella. And this then now continues into grade 9 math and grade 9 science. Grade 9 math kind of continues this theme of learning how to code. Grade 9 science is different, and you can see the curriculum expectation there. Grade 9 science, students are expected to use coding to accomplish something. The actual method of coding is not important. And so we like to say math is learning to code and science is coding to learn. And this can be a really good thing for science teachers because it means whatever way you want to accomplish this is going to work. So the very basics of coding is you actually don't need technology to do it. It's talking to computers and computers are a little bit dumb. So you need to be very explicit. And so this can even be done asking students to break down a lab procedure. Break it down into small enough steps that someone else can follow it without knowing what it is. This can even be as simple as giving them a bunch of Lego, having one student build a Lego piece and try to explain it to another student without letting them see it. See if they can build the same one. And so this is teaching things like decomposition, breaking something down into steps, sequencing, putting those steps in order. If you want to go fairly low tech, but not no tech, this can even be doing equations in Excel, having them program cells in an Excel spreadsheet so that they can turn a cell a certain color if a value is over a certain number. So this can be used to sort lab data, and that's coding. That being said, today I'm going to talk mostly about microbits. So microbits are a very small computer that you can purchase. They're only about 30 to 40 bucks. And the reason why I really, really like them is they allow students of really diverse levels to easily all work together. And they have a really shallow entry point for teachers. So they code in a variety of ways. They're very, very popular. So there's already a ridiculously large variety of projects that students can do that are fully fleshed out and ready to go. And lots of other companies are creating lots of other items that can then tie into the microbit to get even more exciting and advanced. And the website students use to code this is incredibly user-friendly, very easy to figure out. And it has a virtual simulator on it. So even if you don't have enough microbits for your entire class, they can all see how their code is doing. Okay, I believe we have another poll.
Okay, poll number 3.
So have you tried coding so far? Maybe you did in first semester, maybe you've tried it this semester. Okay, we got a big mix here. Nice to know people are trying different things.
Okay, that looks like almost everybody. I will end the poll and share the results.
Great. So a lot of people doing device coding, that's great because that's what I'm going to focus on today, along with the Scratch coding and Python and JavaScript. Those of you that have already done unplugged coding, hopefully you will learn something new. And if you haven't done anything, this could be the thing you do this semester. Can we try the next poll, please? So what do you have access to? Maybe it's in your school, maybe you can borrow it from your librarian. Maybe some of you have worked with Let's Talk Science to get a few of these to try out. Oh, good. It looks like most people have what we need. Perfect.
Okay, I'll end the poll, share the results.
Okay, so it looks like I can focus on microbits and most people are with it. Let's do it. Okay, so here is how you get started. This is how I've gotten teachers in my department started, and this is how you get your students started as well. You basically need to introduce students to 3 things. You need to introduce them to what coding is. You need to introduce them to the microbit or whatever device you're using specifically. And then you need to introduce them to their method of coding, which for microbits is called MakeCode. Introducing students to coding is hilarious because coding is talking to computers, and students are very used to thinking of computers as smart, and they are not. Computers are incredibly dumb, and they will do exactly what you tell them and not what you wanted. So it's a case of malicious compliance. Most students think that what they're saying is explicit instructions, but it usually isn't because humans don't really work that way. And so I usually introduce students to coding by telling them that, and then showing them this video. This video is also a fabulous way to introduce the idea of lab procedures for the scientific method. If anyone's seen it, feel free to, laugh out loud in the chat. But this is a video of a father asking his children to give him instructions on how to make a peanut butter and jelly sandwich. We're not going to watch the whole thing. We'll just watch enough so you get the idea. He follows their instructions to the letter. Take a look.
Now when I'm hungry, I could really go for a peanut butter and jelly sandwich. Do you guys think you can write down some instructions and teach me how to make a peanut butter and jelly sandwich?
Yeah. I'm done.
Step 1. Get 2 pieces of bread out. Got 'em. Get a butter knife and get some PB. Take 1 piece of bread, spread it around with the butter knife.
No, Dad, with the peanut butter.
I'm just doing what it says. It says take 1 piece of bread, spread it around with the butter knife.
Hold on.
Get some jelly, rub it on the other half of the bread.
No, Dad, open the jelly.
Well, it doesn't say to do that. Put the breads together on top of each other. Take a big bite. This doesn't taste like a peanut butter and jelly sandwich. Fail.
Yeah. Oh, yeah.
So the kids get progressively closer, and at one point, the kid almost cries. It's very entertaining. But it shows this idea that we think we've given instructions that are exact enough and explicit enough, but a lot of what we're thinking doesn't actually make it out onto the page. And this is the major problem with coding. So something worth mentioning to your students. Once you've introduced the idea of coding, you can introduce the idea of coding languages. So just like we can all communicate using different languages, English, French, sign language, Morse code, etc., computers understand a variety of languages, but each one has its own grammar, syntax, spelling, things like that. And communication is communication. If you understand how to communicate with someone, the grammar of a language can be learned later. And so the most basic way to communicate with computers is using what's called Scratch or block coding or pseudocode. And this is all of the logical steps without the grammar or syntax. And so we'll introduce that in a bit. So the next thing you want to introduce them to is the microbit or your device. Kids really don't understand what these things are, so it's important to introduce it to them. And you can even do this via a little bit of critical thinking. Have them look at it without the labels and see what they think it is. They'll probably notice things like the buttons or the LEDs, but they might have no idea what to make of the pins, things like that. And so you can introduce the idea that this is a miniature computer. It has various ways to input, like buttons or a microphone, and various ways to output, like a speaker or an LED screen. And it will do whatever you tell it to. Please be aware, the microbit, if you've tried any of the sensors, they are not lab grade. The temperature sensor is nowhere near as accurate as a thermometer. So they're good, but they're not perfect. So once they've been introduced to the idea of coding and to the microbit, you want to introduce them to the actual way they are going to code this device. And for microbit, that is the Make Code website. So let's head there and take a look. So this is the Make Code website, okay, that you're seeing right now. Yep. And when students join up, it basically creates an account for you tied to your computer. So if you go to a new computer, you're not going to see any of your stuff. And if you scroll down, one of the first things you see is tutorials. The best way to get your students started is to have them do 2 or 3 tutorials. And it really takes them through in a very basic way. So I'm going to click this first tutorial here, flashing heart. And notice it gives me an option. I can use blocks to code, which is the simplest method, or I can use these two programming languages, Python or whatever else I'm looking at, JavaScript. And so if you start the tutorial, it tells you what you're going to do. You're going to make a flashing heart. And you can notice in our simulator here, we've got our blocks. So this is how we actually put commands to the microbit. We've got our workspace here, and we've got our virtual microbit over here. And so you can do things like drag a block and they click in, and then I can show what is happening here. And these clicking are going to make a smiley face, very tall smiley face. And you can see it has now updated to my virtual microbit. The tutorial at the top here shows you exactly what to do, and students follow that with pretty much no issue. And the way I started this is I just followed the tutorial myself. And once students are comfortable with the tutorial, they start to feel more comfortable experimenting. So if I go back to the main page here, if I click a new project, you do have to name it first. Okay, that is a requirement and teaches kids good naming principles. Notice I now have 3 smiley faces. So that's a good long enough name to find again. And you'll notice now I have a lot more options of commands. Students will slowly learn what these are as you use them, but a lot of them make perfect sense. So I have one show string in a word. I have clear screen. These are pretty good at making sense to people. Others are more challenging, but you'd be surprised how much students are willing to experiment once they get kind of their feet under them here. And they get that from just doing 2 or 3 tutorials. Okay, let's jump back to this. So once they've done a couple of tutorials here, let's actually make this full screen again. There we go. So once they've got a couple of tutorials underneath them, like the flashing heart or the name tag or continuing on, they start to feel a lot more comfortable doing this. And I would encourage you to explore several tutorials before doing it with your class, just so you feel more comfortable with it. After that, you do need to show them how to take their code. And so you can see the code here. It's going to show LEDs in a heart. Then it's going to show LEDs blank. And it's going to do that forever, which means it's going to endlessly repeat those 2 instructions. So once they've made their code, because this is an actual physical computer device, you need to show them how to download their code. This does require a USB port. So if any of your students have some Macs, they might not have a USB port. So they might need an adapter, or they might need to kind of email their code to a friend. There are lots of videos online about how to do this and good instructions on the microbit website. So not hard to show your kids one of those videos so they know what to do. So specific ideas, what do you do with this? So here are several things that I've tried, along with several things I intend to try and haven't gotten to yet. So for the chemistry unit properties, a great thing you can do is code a conductivity tester. This is basically asking the microbit whether it has made a complete circuit or not. And then you can dip wires into various substances and actually see how conductive they are, or if they're conductive, period. I haven't come up with too many other things for the chemistry unit, although if someone has one, I would love to hear about it. For the electricity unit, you can kind of continue the theme. There is an expectation, a specific one about insulators and conductors. So you can have students test various materials, and that's what you're seeing in the picture on the left, is my students checking that copper wire to see how conductive it is. And you can take this even further once your students are comfortable by actually coding a battery tester to tell you how much juice is left in your batteries. For ecology, there is a whole host of things you can do because there's lots of sensors on the microbit. There's temperature and light sensors. And so you can use those as an opportunity to talk about abiotic factors. You can also talk about things like urban spaces. So is the temperature higher on the pavement versus on the grass on a hot day? You can also code a animal tracker, which uses acceleration in the X, Y, or Z direction. And you can use the radio signal function, which could be an opportunity to talk about actually collecting data in ecology and how we might have to leave sensors set up in places that humans cannot stay. You can also code a moisture sensor. You can either buy an actual moisture sensor device, or you can code it simply as an advanced version of the conductivity tester by using just 2 nails, 2 paper clips, and some wires. All of these are basic enough that students with no experience can copy the code that exists online. So there are tutorials for all of these, and they can be successful at it with virtually no help from the teacher. Just encouragement, basically. For the astronomy unit, once again, you've got quite a few options. You can actually combine this with Let's Talk Science's Living Space, which is where you compare your class environmental conditions to the ones on the International Space Station. So that's using the temperature sensor for the microbit, as well as a separate sensor they can send you in order to test relative humidity and CO2 levels. Also relevant with COVID. You can combine this with the other Let's Talk Science project, Tomato Sphere. So talking about soil moisture in the tomatoes that potentially would grow on the International Space Station. You can also use the radio signaling, talking about getting data from our satellites orbiting the Earth, as well as the shake sensor. So when you shake the microbit, that's another form of input. It will do something. And so this can be a way to talk about space junk. How do we deal with space junk hitting the International Space Station or hitting our satellites in orbit? How do we know it happened? What do we do then? So these are just some of the specific ideas that exist. These are all ones that I would consider easy enough for absolute beginners to do. I would know because I'm a beginner and I did them. I see in the chat from Suzanne, are all these ideas on the MakeCode website? Almost all of them are, I would say. Some of them I have also cobbled together from other teachers' blogs or following some other teachers on Twitter. All the ideas, I would say, are on the MakeCode website in various levels. The conductivity tester on the MakeCode website is very basic, which is totally fine. But I recently saw a teacher on Twitter who had done a much more advanced version with a bar graph to show how conductive something was. And that one isn't on the MakeCode website, although I'd be happy to share it with you if you'd like.
We had another previous question from Emily, up a little higher.
Yeah. A little higher.
Yeah. Do you have?
Oh yes, Emily, about durable. Yeah. So I've also tried the Inksmith kits. I agree, they're kind of fragile. Because this stuff is so relatively new, a lot of the things people are putting out, we're seeing how fragile or durable they are. It can also be a good opportunity to talk with your students about the fragility of equipment. And I know in particular, there was one piece of equipment I was using last semester that one of the pins broke off, and it was a great opportunity for a student who knew how to use a soldering iron to solder it back on. So yes, I have not found things that are incredibly durable at the moment, but I'm on the lookout still. I think as things progress with this, as it becomes more and more common, I think the durability will come.
Do you talk about the header that you can plug the microbit into that gives you access to like a breadboard to plug in wires and that sort of thing?
Yeah, and like the peripheral. So there's like a water pump from Inksmith Climate Action Kit that can break quite easily, as well as their soil moisture sensor. Their latest Energy Climate Action Kit has a photoresistor that you could just snap right off if you're not careful. Mm-hmm. So they're not fabulous yet, but it's going in the right direction, I think. And I see Emily's other question. How do you go from just copying code to actually understanding what they're doing? Yeah. Consider how you learn anything, right? Copying what you see and then learning to understand it really is the first step. And I found it actually was a great first step for students that were almost paralyzed with fear at the idea of coding. It really freaks a lot of students and teachers out. And so I started the same way. I started copying code, and like you, I was wondering kind of what the point was. But as I became more comfortable copying the code and figuring out what the code did, I then became more comfortable, and so did my students, with going off book, so to speak. So for the conductivity tester, for example, which is kind of the most basic thing, that's where I started. You basically do a code that says, when the pin is touched, show an image. And students could all do that. They could all pick their own image. But then other students started to think, they're like, well, but then you can't reuse it. You have to like restart the microbit to use it again. And we were all like, yes. So what could you do? And they found the clear screen function. But then it was clearing the screen so fast they couldn't see the image. So they learned about the pause function. Other students liked the image, but also found they could get the microbit to play music. So they did that. And so as students became comfortable exploring, they slowly advanced and learned what more and more functions did. So I think starting from copying code, as basic as it sounds, is a good starting point. It's like starting from doing a recipe when cooking before you start experimenting and figuring out what all the recipe steps actually do. So it's essentially the same thing. Sarah, I will be sure to try to share the bar graph conductivity one.
A couple of tips I can give. The first one is to break your code. So after you've typed it in, what happens if you remove a block or change it or replace it with a different block, and then look at the differences to try to understand what's happening. And then the second recommendation is to extend your code. So once you've written it, what else can you do to that code to make it do something else or make it do something more?
Mm-hmm. Absolutely. And I see Mark definitely getting students. So I had students coding a temperature sensor in the lab, and we used that to talk about the temperature inside, outside, in different ecosystems, things like that. It was a hook. It was a link to application. It also brought a new light to every single device we use in class. The idea that someone had coded that to make it work. And so I thought it was a really good first step to coding for students who maybe hadn't really been introduced to it before. Or at least half my students had been introduced to coding, but not to physical computing. So they were used to code that programs a game on a computer. And they sort of didn't realize that code could come off of their computer into a real device. It's also worth noting, and I'll just kind of switch back to make code for a second. It's worth noting that students can really go quite far with this, because as students are coding, so if I open up a program I've made here, so see if you can figure out what this code does. It shows the icon smiley face. It pauses for half a second, clears the screen, waits another half second, and then repeats forever. So you can see I get a flashing smiley face. For students who are advanced, they can switch from the blocks to JavaScript or to Python. And so a lot of students I had that had already learned how to program started working in Python. The neat part is that if they're working in Python and they're not quite sure what they're doing, or if they've made a mistake, they can actually change things in Python and switch back over to the blocks to see how they did. And you can see here that my pause now is 1000 milliseconds, not 500, because I changed it in Python. So this can be a great way for students to slowly start exploring an actual programming language instead of the block coding, which is also known as pseudo-coding or fake coding. So that's a pretty great thing. And so here's kind of a close-up view of one of these SNC1W coding ideas. It is the conductivity tester, and you can see the really basic version on pin 0 pressed, show this icon. This isn't even the most basic version because my kids added the pause and the clear screen so you could redo it. A way more advanced version is starting to use variables. And you can read all about this. You can start by copying code like this exact one. So this says, make a variable called current. Set current to whatever pin 0 says. And then plot a bar graph of that up to this number, which is the maximum number the microbit can display. And so here you can see a bar graph being displayed. Whatever item I was testing here is mostly conductive, but not as conductive as it could be. And so that's just kind of an idea. And you might have students doing both of these in the same class. When I first tried this in my classroom first semester, I had students doing the very simple version, which I understood. And I had some students doing the advanced version, some in Python, which they had to explain to me, although they were happy to do it. So huge variety of entry points for this that doesn't require you to be the one to differentiate it, which is great. Okay. Any last questions about coding or any of these specific ideas? I'll just jump back to the ideas. Or if anyone wants to share their own ideas before we move on to engineering design process.
Could you just go back to the next slide, please?
Yep.
Yep. So something that I would recommend you concentrate on, do you see where it says set current to analog read pin P0?
Mm-hmm.
So that is all about an analog input, and I assume it's going between 0 and probably 5 volts, right? So that's where you can get sensors involved. So one really simple thing you could do is get a potentiometer, which is a variable resistor. And so when you're teaching the electrical unit, for instance, you can adjust the potentiometer and then have that signal going in and then graph it on the microbit.
That sounds amazing, and I'm going to pretend I understood all of it.
Yeah, and then there are literally hundreds of sensors out there that work that exact same way. They're basically just variable resistors on the inside. Some of them are to measure loads like forces. Some of them are to measure pressure, some to measure acceleration. So there's various sensors out there.
Great.
And not that expensive. You can go on Amazon and get many sensors for under $5.
If only my board would let me purchase on Amazon. Okay. Welcome to the second half of our presentation, engineering design process. Can we launch our last poll, please?
Poll number 5.
So I asked you about coding. This is the other half. How familiar are you with the engineering design process? About the same.
Okay, I'll display the results now.
Okay, so a bit more familiarity, but still quite a lot of what is this, which is fair. That's why you're here. So you can see the curriculum expectation up there. The engineering design process has been slotted into this new curriculum right alongside scientific inquiry and scientific research. So it's been hugely prioritized by the new curriculum, going alongside those two things that we love in science. The good thing about the engineering design process is it's something you probably were doing anyways without naming it. It essentially is open-ended problem solving to make something. So it's not necessarily an experiment or anything like that. We're not trying to figure out how something works. We're trying to make a thing that does the job. And this could be a physical thing, this could be a process, this could be something like that. And it's really good for having students solve both big open-ended problems as well as really specific problems. The key features of the engineering design process is that students have to define exactly what they're looking for. So key criteria as well as key constraints they have to work under. And it's the idea that you make a product, test it, and then refine and redesign it based on your tests. So when do I use this? Anytime the goal is for students to make something, you could potentially use the engineering design process. The problem is that it takes time. You have to give students time to think, time to build, time to test, time to rebuild, time to retest. There's no real way to shorten that. And so if you're trying this for the first time, you probably want to do it once really well, as opposed to trying to fit it in everywhere and kind of only half do it each time. So this is a great video by Science Buddies. We are not going to watch the whole thing, just the end, but I highly recommend you do watch it. It really contrasts when we should be using the scientific method, so the inquiry process, versus using the engineering design process. So let's take a look at the end of this.
There are many other problems or projects where science and engineering can be combined. When you are not sure which process to use for a project, follow these general guidelines. If you ask, "Why does this happen?" or "What would happen if?" you need to follow the scientific method. If you ask, "Can I build something that?" or "Can I build a better something?" you need to follow the engineering design process. Thanks for watching, and happy creating and experimenting.
Okay, so a great example here. I normally do a physical and chemical properties lab where I have students determine how physical and chemical properties of contaminated water change if they filter it. So I have them build a filter and then prove to me that the water sample has been cleaned based on its changed physical and chemical properties. It's super fun. But the point is not the water filter. The point is the physical and chemical properties. And so we use the scientific method for that. If I wanted to change it to be about engineering design process, I would make it about building the most efficient water filter. And they would have to build it multiple times. Don't do that. There we go. So these are two more kind of graphics that I found on the internet about the engineering design process. You can see on both of them, we're defining the problem. And so this could be very simple. You might tell the students what the problem is, or you might give them a really broad question like, how can we help with climate change? How can we help with reforestation? And then they might have to define, well, what is the actual problem they're going to try to solve? So it can go big or it can go small. Chantel, I absolutely can share the filter activity with you. You'll notice in the graphic on the right that there's arrows kind of going from every step to every step. This is really like the scientific method. It doesn't need to go in order. It often will bounce back and forth depending on what students find. But the same parts are in every graphic. This idea that students build, test, rebuild, and retest. So that's really your keys for the design process. So here's how you can do it. You'll notice the two pictures kind of at the top on the left. That's something that I did with my students in SNC1W last semester, and I'm planning to do it this semester, in addition to a bunch of other schools that we're going to have a little competition about. And it's wind turbines. I love this as a design project because it's very specific. So I didn't have students going all over the place. Eventually, I'd like to open it up more, but as a starting point, this was really good for me. And it tied into both the electricity unit, which has specific expectations about power generation, and it ties into the ecology unit, talking about renewable energies and how those are going to serve us in the future with climate change. I had students use DC motors, which you can buy from anywhere. And we just put corks on the DC motor, and they had to build a wind turbine, either vertical or horizontal axis. And then they measured the voltage that was coming off of their wind turbine. So this gave them an actual measurable goal of how well they were doing. And you can see some various iterations that happened there. And this project took about a week. Between the idea of introducing wind turbines, having students research what makes good ones and what makes bad ones, having them plan various ideas, having them pick their idea, build it, test it using the fans. You can see my little tape marks on the lab bench there. We standardized the test. Then they reinvented their design based on the test and what they saw in other groups, rebuilt and retested. Some groups did that more than once. I also then had them write up a report about comparing wind power to various other types of power, which also checked off a bunch of other expectations in the electricity unit, which was nice. Other ideas that I have come across, so I have not tried any of these, although I know some teachers who have. There's also links in pretty much all of these pictures to actual descriptions of these ideas, so feel free to click on those later. Mushroom packaging, all you need is mycelium, which you can actually buy. And students can talk all about renewable packaging and the plastic crisis that's currently ongoing, which ties into a bunch of ecology expectations. They can do lunar landers, which is a very advanced version of the egg drop experiment. And this can be used to talk about rovers that we've sent all over the universe. This can be used to talk about launching satellites from the International Space Station, etc. You can have various problems they need to solve here, either a soft landing or landing in a target zone, things like that. Environmental monitoring. So this can use the microbits, measuring temperature, relative humidity, measuring sunlight and hours of the day. This can also be tied into then zero energy housing. So have the students attempt to build a house that keeps cool under a bright light or keeps warm at nighttime. And so there's a whole bunch of ideas that you can go with here that all tie into the SNC1W curriculum. You can also talk about sort of greening our cities and sustainable development when it comes to most of these as well. And if you want to go for extra brownie points, you can try to tie these into the UN Sustainable Development Goals, which is really fun and very doable. I see we've got a bunch going on in the chat. Let's see what we got here. Filter, filter, filter. I will definitely share that. How do you measure voltage output of the wind turbine? Yeah, you just, if you have multimeters or voltmeters, I suppose, you literally hook up the two clips of the DC motor to a voltmeter and it will register the voltage as the motor spins. So motors kind of work in both directions. If you put electricity in, they spin, but if you spin them, they put electricity out. So it's really easy to do. You will be limited of your voltage based on the size of the motor. So my students were initially quite excited. They thought they were going to like power their laptops using this, but the motors I got are quite small. And so they're not even quite enough to power an LED. If I was doing it again and had more money, I would have bought much larger DC motors, which would then produce more voltage. The mushroom packaging idea, Tram. Yeah, you can actually click on, if you click on the image in my slide deck of the mushroom packaging, it will take you to the actual project, which I found online. But basically, you can talk about alternatives to plastic and you can ask students to design packaging, maybe that's insulating. So packaging that will keep, you know, a cup of coffee warm for a certain amount of time, or packaging that will hold the most using the least amount of mycelium. So you can have various criteria there that you're going for. And Chriselle, how do you balance the time to do a project like this with a jammed curriculum? Absolutely. It's very hard. And I initially didn't want to do it. I'll be really honest. I like to cover all my curriculum. Not that I can, not that anyone can, but we try. I basically went out on a limb last semester and decided that this was in the new curriculum. I was going to try it and see how it goes. And I was actually quite surprised at the amount of learning that went on and how into it the students were. I wouldn't do it probably multiple times a semester because I do feel like I need to cover more curriculum. but I feel like doing it once really well is well worth the time. And so I did have to cut some other things in order to make it fit, and that happened, but I feel like it was a really good use of time. Depending on what you do, you also could probably cut that week down to like maybe 3 days, depending on what you're doing, especially if you make them do a lot of like research and brainstorming at home. Because this was my first time doing it and my first time having a class with some wildly different levels of students, I wanted to kind of see it all happen and make sure that I was there to facilitate as they were working. So I kept all of it during class time, except for the report at the end. So that did take kind of the full week, but you probably could cut it down to 3 days, maybe, if you tried. Oh, building fire extinguishers. Jennifer, yeah, with vinegar and baking soda. I've done that one as well. And thank you, Peter, for microbit sources. Yeah, absolutely, Chantal. I can share, I think at the end of the presentation, my email will be up on the screen and my social media. If you want to contact me, I'm happy to share these things with you. And Lise wants the slide deck link. Perfect. Oh, thank you, Peter. Yes, that's my email. Feel free to contact me. Okay, so these are the ideas of what to do, but how do you do it? So that's the next bit, and I'm gonna rush through the end here because I'm running out of time. So the key of the engineering design process, like the scientific method, is that it has steps. When students do the scientific method, you can usually watch them do a lab or see their lab report and know that they've done the steps. With the engineering design process, it is exactly what it says. It's a process over product. And so you need a way for students to make their thinking during the process visible to you. And you can do whatever method you want. I just kind of took all the steps of the design process and put them on a sheet and asked students to record their thinking, whether it was diagrams, words, whatever. In the future, I'd probably broaden that even more. I'd probably say they could do videos, pictures, things like that. But you need a way to make their thinking visible during the process, because that's really what you're looking for in the engineering design process. If you're feeling really advanced, feel free to co-construct these criterias with your students. I just gave my students what I was looking for. It was the first time I was doing it. You have to keep it simple. Also know that this requires group work. There's really no way for students to do this on their own because more heads are better than one. So I needed a way to kind of score out and figure out if the groups were working well together. Partially, I just did this by observation, but this is actually one of my favorite methods for helping evaluate group work, so I thought I would share it with you. I call this the team contribution report. It has a few questions at the end asking students how well they worked together, what they would do differently next time, any challenges they had. But at the top, it asks students to list themselves and their group members, what everybody did, and a score out of 10. What prevents them from just casually giving everyone 10 out of 10 is that I only give them enough marks that if everyone did the same contribution, everybody gets 8 out of 10. If someone deserves a 9, that mark has to come from somewhere. Someone else has to get a 7. And I find this forces students to think a lot more deeply about how their group work scored out. And of course, these are private, only I see them. I don't necessarily make mark decisions on these, though sometimes I do talk to students if they get a particularly low score from their group to make sure that they actually understood what was happening. So this can contribute to your assessment triangle of observations, conversations, and products. Tips for this so that it goes well. Tip number 1, you need to help students brainstorm. They are surprisingly terrible at it. I was very surprised. Think, pair, share is, a really basic one I think most people know. You can also start to get a little more exciting. Let's Talk Science has some really interesting ones like Crazy Eights and Carousel Brainstorm. I have run out of time here, so I'm not going to explain them, but I have included links here. Feel free to check them out. It also, as I said, just takes time. They need time to think. They need time to build. That time doesn't necessarily all have to be during your class period, but they do need the time. Otherwise, it's not really worth doing. And the last bit is consider your situation. When I had students doing the wind turbine project, one of the criteria they had to follow was that their turbine had to fit on the motors I had. They couldn't build a really big turbine. The motors were small. Likewise, constraints. They might have to complete it in a certain amount of time. You might only have so much tape. You might only have recycled materials. If there's anything about your situation that students need to know, you need to make sure they know it before they start. And your last bit, as I said, is you need some way to see what they're thinking and what they're deciding. So any way to make things visible for yourself and easy to mark. I also highly recommend putting both ideas together. If you're making a lunar lander, instead of putting an egg in it to prove there was a soft landing, you can code a microbit to register gravitational force. And if there's too much gravitational force, it can tell you it did not survive. And there's a link there to that one in case you want to try it. You can also try using Inksmith's Climate Action Kit to make a smart watering system. I actually did this one in my ecology unit last semester. So students code a smart watering system to only activate a water pump when soil is dry. And this ends up talking about vertical gardens and hydroponics and aeroponics. It's recommended that students actually build their own vertical garden to go with this, but I didn't have time because who has time? So instead, my students did the coding and engineering bit, but then they just designed their vertical garden. And so you can see here, this is one that one of my students made, well labeled, shows the integration of the smart watering system. But this saved many days because my students did not have to build anything physically. The last bit is please remember to be kind to yourself. You might be totally starting out and had no idea what coding was before this curriculum change. You'll get there. I've been progressing slow but steady. You just have to be willing to try. And you have to be willing to accept that a lot of the students are going to be ahead of you. But they are okay with that. And so you have to be okay with it too. Pick something and start. That's all it takes. Just pick something and start. Okay. We have hit the end now. I'll take any questions, but before I do, I just want to mention for Steo, because, you know, I love them. Steo's having a in-person conference again in Toronto, actually in Etobicoke at Humber on August 15th, 16th, and 17th. Mark your calendars. I will probably be there doing something. So feel free to come say hi. Okay, this is me. I love to connect with people. So like I said, feel free to contact me. Anyone who wanted me to share anything, shoot me an email, message me on Twitter, anything like that. I am happy to share. Okay, we're all kind of on the same team here. Okay, so I'm going to be respectful of your time. If you have to go, thank you for coming. It was lovely to have you all here with me, and hopefully you got some ideas of how to move your own teaching practice forward for the SNC1W.
Don't leave just yet.
But otherwise, over to Peter, and I will quickly look in the chat to see if I missed anything.
Okay, let me take over. Okay, so I have dropped some links into the chat. The link for the presentation again. I've also provided a link to the OTF Connects Calendar, so you can look for future sessions, as well as the link to the survey. So if you don't get a chance to fill it out right away, you will receive an email within a day or two. What I'm going to do tonight is compile notes from our chat, and those will be included in the email that you receive tomorrow or the next day, as well as a link to the video of this session. And with that, I would like to thank Laura. That was very interesting. I love that you've used the microbit to approach this new curriculum. The microbit is a fantastic, physical computer for introducing programming concepts, and I particularly like that you can use block programming or Python. I wouldn't recommend JavaScript personally for this, but Python I would. And Python will get them like into grade 10 computer studies, for instance, or many other extensions like Jupyter Notebooks, which is something a lot of science teachers are starting to use. So yeah, I'm glad that you took the approach that you did. So with that, thank you so much. And thank you to everyone for attending. We really appreciate it.